Alrighty, in today's lecture, this will be going over lesson 8.4, trigonometric equations. All right, in this lesson, you will kind of see as you overview the reading that there's not much new material. We're just using everything we have learned from chapter 8 to help us solve different versions of equations of trig functions. So I'm just going to try to jump right into the homework style questions and just help you answer those questions. All right, so if we start with number one, it says 2 sine x plus 1 equals 0. Now, on your homework, there are some of them that just simply ask, is there a solution? Some will ask, like, is this a solution? And they'll actually give you the answer. I think I found a couple. I found, yeah, a couple, well, really just one, where I can apply that. But really, when you end up with those type of questions, just simply plug it in and just see if it equals that value. Do watch out because a lot of times you'll plug it in and go, "Oh, I got a number, so therefore it must be equal." Not necessarily. You can still plug it in, get a number, and it give you like the opposite sign. So make sure when you get to those type of questions that you plug it in and then work it completely out to make sure it equals what it's supposed to equal. And then there's two other type of questions, and I'm going to try to hit both of them within each one of these questions. Some of them are just going to be asking for the answer between 0 and 2 pi. So you would just have to find all the answers that apply um, within the unit circle. But if it asks for all infinite amount, you just have to add in a plus 2n pi to your answer, except for tan and cotangent. Since the period is a pi, you would apply n pi, where that n just represents all integers. So like 1, 2, 3, 4, 5, depending on how many times you want to go around the circle to get an answer. All right, now I'll kind of explain all that. But again, depending on how your question is asked, it depends on how the answer should be given. But I'll try to give both. All right, but for starters, you just kind of need to solve these guys. When it's just one trig function, it's super easy. The idea is to isolate it. So I'm going to subtract 1, divide by 2. And then technically here, you're taking the inverse of this guy right here. But in reality, you're really just asking yourself, sine of what number will give me negative 1/2? So you want to go here on your unit circle. Sine deals with the y, so it's either going to be in quadrant 3 or in quadrant 4. Sine being the y value would be when it's furthest away from the y-axis. So I'm looking for this answer and this answer right here. And then it usually does ask it for it to be in radians, but there are certain questions, and I'll find some in the book as well, that ask you to put it in degrees. So you just have to have your answer in 0 to 360 type stuff. All right, but this right here, it's 30 degrees more than 80. So this would be a pi 6. So this would be a 7 pi 6. This coordinate is negative square root 3 over 2, comma, negative 1/2, which is what I'm looking for. This would be pi 6 away from a full 2 pi, so this would actually be 11 pi 6. And this right here is the square root of 3 over 2, comma, negative 1/2, which again is what I'm looking for. So for this example here, your answer is 7 pi 6 and 11 pi 6. And if it just says it wants answers from 0 to 2 pi, this would be the answer. However, this doesn't. So in this one, I want all of them. So what I'll have to do is just say plus 2 in pi to both of my answers. So if the question does not ask from 0 to 2 pi specifically, this is what you have to add in there. Now, I think also on your homework, it wants both answers. So I think like one step would be this one, and then the next step wants the end. So you would write it without this part. The next answer, you would write it with this part. Right. And of course, if you have questions on how to enter it or just answering the question itself, feel free to reach out. And of course, I can answer those questions. All right, let's look at another one. Let's look at number 2. This one says 4 sine squared x plus 2 equals 3. So again, one trig function. I'm just going to isolate it. So I'm going to subtract 2 on both sides. So I get 4 sine squared x equals 1. Divide by 4. So I get sine squared x equals 1/4. To get rid of a square, I'm just going to take a square root of it. All right, so therefore I get sine, oop, that's not a sine. I get sine x equals 1/2. And so when I'm looking at this right here, again, I go to my unit circle and I look for where the answer ends up being 1/2. And so again, 1/2 being y, that's going to be the furthest from the y value. So that's going to be located here. Oh, maybe a little bit further down, about right here. And again, it's positive, so it's going to be either in quadrant 1 and 2. So this right here would just be pi 6 because the coordinate is square root 3/2 comma 1/2. This guy right here would be 5 pi 6 because it's 1 less. And this right here would be negative square root 3/2 comma 1/2. All right. So again, when I'm writing my answers out, again, I'm looking for what value gives me this value on the unit circle. So x would equal pi 6 and x would equal 5 pi 6. Again, if it was asking between 0 and 2 pi, I would be good to go. You know what? Actually, I forgot the golden rule. Anytime you take the square root, don't forget plus or minus. So I also need these answers, which again is a 11 pi 6th, and this would be 7 pi 6, because that's what we saw on number 1. Now, if it was asking from 0 to 2 pi, you would then write all those results down. So you would say they had 4 answers. So where sine x equals plus or minus 1/2. Again, when we take a square root, don't forget the plus or minus. Now, because it's looking for infinite many solutions, what happens here is because from here, let me get a different color. From here to here and from here to here, that's a half circle. So that would only be pi away. So instead of saying plus 2 n pi, we would just say plus just n pi. So when it's asking for the values of n, like for infinitely many solutions, this is what it would want. If it was asking all the answers between 0 and 2 pi, you would write these 4 answers. But now the reason I don't include this one, because if I take this answer and I add a pi, I'm here. If I add another pi, I'm back here. And then so on and so on and so on. Same concept with this one. If this is one answer, if I add a pi, I'm back over here. And if I keep doing that, I'm just going to keep getting these same solutions over and over again. All right, so watch out for questions like that. So this was a good one to go over. Next type I want to look at is number 6. Number 6 says sine 2x equals square root of 3 cosine 2x. All right, so what we want to do here is try to use some of our trig identities to make life a little bit simpler. So what we'll look at is we'll go back and look at our double angles. So before I go into that, let me just make sure there wasn't an easier way. No, that'd be if there's only one. I'm thinking we're gonna definitely have to use the double angle. Yep, I'm not seeing any tricks of the trade. All right, so we'll fly back to double angles. Double angles would probably be in the beginning of 8.3. So we see that sine 2x is actually equal to 2 sine x cosine x. And then cosine 2x can be one of three things. Which one would probably be the easiest? I'm going this direction. I'm going to go with 2 cosine squared x minus 1. We'll see where that takes us. All right. So with that, I get 2 sine x cosine x. Distribute this out. So I get 2 square roots of 3 cosine squared x minus square root of 3. Let's get all of our trig function on one side. So this would be 2 sine x cosine x minus 2 square root of 3 cosine squared x equals negative square root of 3. Would this be getting any easier? So I can see I could probably take a cosine x out. Be left with 2 sine x minus, actually, let's take a 2 cosine x to have just a little bit less to deal with. So this would just be a sine x minus a square root of 3 cosine x equals negative square root of 3. Let's see. Let's take this right here. So we'll take this and this equal to this. So 2 cosine x equals, I don't know about this one because I could say it equals negative square root of 3 or the other one, but that only works with the zeros. Let's go back to that double angle of cosine. You know what? I think there is a better alternative. So these questions are really good, and you'll see this happen a lot throughout this process. You'll start one way and kind of go into a dead end, and then you would want to go a different direction. And here is what I'm thinking now, because that's going to give us a very long process that just looks pretty gnarly. Again, the goal is to get to one trig function. So since there's no adding or subtracting, what I'm actually going to do is actually divide by cosine 2x on both sides. And the reason I would do this, because sine 2x divided by cosine 2x using the quotient identity is the same thing as tangent of 2x equal to the square root of 3. So then using, actually, I don't even want to use the double angle at this point. What I can do is say, all right, tangent equals the square root of 3 where on the unit circle. All right, so we know that tangent's equal to 1 here. And to be positive, it has to equal something over here as well. So square root of 3. So there's three main ones, right? This would be the square root of 3 over 2 and 1/2. This is square root of 2 over 2, comma, square root of 2 over 2. And this would be 1/2, comma, square root 3 over 2. We know this one ain't going to be it because this will equal 1. But if I keep change flip, this will just give me square root of 3 over square root of 3, keep change flip. This one, this one here, again, if I keep change flip, so that'd be square root of 3 over 2. Well, actually, let's flip that again. Hold on. Tangent is equal to sine over cosine. So I actually need this one here. So that would be the square root of 3 over 2, comma, 1/2. Keep it, change it, flip it. and then I get square root of 3. So this is my winner right there. And again, tangent's not one that I just always have memorized. I just know that there's one that's 1, one that's square root of 3, one that's square root of 3 over 3, and then I just kind of have to quickly do it in my head. But just kind of show you, tangent here would be the square root of 3 at this marker here. And it will also be at this marker here as well. So that would be then meaning that 2x equals that marker. What is this marker? Pi thirds. Oop, pi thirds. And then 2x would also equal, so this is 60, 120, 180, and this would be 1, 2, 3, 4. 4 pi thirds. And then we would just simply divide by 2. So x would equal pi sixth. And x would equal, what's that going to be? 4 pi 6, which is 2 pi thirds. Here's the issue, though, when coming up to this type of question, is again, if it was asking for all of the solutions between 0 and 2 pi, this would be the answer. The issue comes up with is that since this right here, get a different color here, goes from here to here is just 1 pi. I don't have to keep writing out all these answers. I can just say plus n pi and then be done with that part there. So therefore, this would be my answer. If it again asked from 0 to 2 pi, then you would write both of these responses. All righty. Actually, no, because that would be you here. Hold on, let's look at that a little bit more. I think the issue is from here, because I divide it by 2. So, okay, at this point, 2x would equal n pi, and this would basically be the same answer if I added n pi, because that would give you 4 pi thirds. All right, but then when I divide that by 2, I would technically have to divide this part by 2, so it would actually be n pi divided by 2. That right there, if I was to add 1, would give me 2 pi thirds. And then if I added another one, because again, that right there would give you 3 pi 6, and then 4 pi 6 was 2 pi thirds. And then I could keep adding that over and over again. All right, so in the situation, since there, I had to, again, if I was just looking for answers between 0 and 2 pi, this is it. But was asking for those infinite ones, it's wanting a more simple form. But because I divided by 2 here, technically I had to end it here so that I could divide by 2 as well. So we'll do some more of this right here because this infinite one can become a tricky situation. All right, let's look at another one. Let's look at number 8. This right here would be sine squared x minus sine x equals 2 sine x minus 2. All right, when you have a lot of the same trig function, the goal is to get everything to one side. So I'm actually going to subtract 2 sine x and add 2 to this side. And when I do that, I will get sine squared x. Negative sine x minus 2 sine x is minus 3 sine x, because they're like terms, plus 2 equals 0. Now, if I just had just sine and not this square here, I would have left the 2 there. But with this square here, this should be an indication that we might have to use what we call U substitution to be able to factor this. So what we're going to do is we're going to say U is equal to sine x. So this becomes u squared minus 3u plus 2 equals 0. Now I have a nice quadratic where this will be u, this will be u. Two numbers that multiply to 2 is 2 and 1. If I wanted to add to negative 3, they would both be negative. So then I get u minus 2 equals 0, u minus 1 equals 0, u equals 2, and u equals 1. I will answer this question. A lot of my students always go, do we have to use u? No, you can technically use whatever letter you want. You're just substituting it in for something to make it more of a quadratic that you're more familiar with. Once you get to this point, you just substitute back in. So this becomes sine x equals 2 and sine x equals 1. So again, if I'm trying to solve for x, where on the unit circle does sine equal 2? Well, hopefully you're saying, I thought it only went from 1 to -1. You would be correct. So this right here would not be a realistic answer. So then I move on to the next one. Where does sine equal 1? And it happens in one location, and that would be at pi halves. And again, if this was asking between 0 and 2 pi, you would be done at this point. There is no extra little numbers there to divide that in or anything. So this would just be 2n pi because it would take one full circle to get right back to it. So there's no like on this side type of thing of what we've seen. So this would be your final answer here. Right? All right, let's look at another one. Again, trying to give you all the examples that you would need. So looking at number 9, it says the square root of 3 tan x plus 1 equals -2. Again, when it gives you just one trig function, the goal is just to isolate. So I'll subtract 1. That gives me -3 divided by square root of 3. Rationalize that. Which just gives me that. So again, on the unit circle, I want a negative, so that only happens in quadrant 2 and quadrant 4 for tangent. All right, so for negative, I know it's not going to be the middle, the 45, because that's going to be 1. So it's either going to be here or here. And again, this right here would just be -1/2 square root 3 over 2. And then this would be negative square root of 3 over 2, comma, 1/2. So again, keep change flip of the y divided by x. If I keep this one, change the multiplication, flip this will give me this one right here. So this is my winner. So again, that'd be square root 3 over 2, change, flip. So then that would give me the negative square root 3 I'm looking for. All right, so this value, and again, it would also happen right here as well at 1/2 comma negative square root 3 over 2. But again, we're looking for infinitely many. So I'll kind of show both so that you have both examples. But this right here would be 2 pi thirds. So that'd be x equals 2 pi thirds. Down here, this would also be 3, 4 at 5 pi thirds. But again, since this specific problem is asking for all, you would just have to add in a n pi to this answer here. So again, between 0 and 2 pi, here's your answers. For all answers, I had to add this n pi because to get from here to here and infinitely keep going, you'll just keep hitting both of these marks. All right, so let's see if we can go a little bit harder. Let's go 10. All right, number 10, we have 3 tangent squared x minus 1 tangent squared, x minus 3 equals 0. Now this one's real nice. It's already factored for us and set equal to 0. So all you have to do is set each factor equal to 0. So this becomes 3 tangent squared x minus 1 equals 0. And then tangent squared x minus 3 equals 0. So I'm going to add 1 on this one. So I get 3 tangent squared x equals 1. Divide by 3. I then get tangent squared x equals 1/3 square root. We're not going to forget our plus or minus this time. So this gives us plus or minus 1 over the square root of 3. If you rationalize that out, you get plus or minus the square root of 3 over 3. Over here, I get tangent squared x equals 3. So then your question is, from this, add 3. I got distracted there. Take the square root of both sides. Don't forget the plus or minus. So that means tangent of x is equal to plus or minus the square root of 3. All right, so this is pretty much going to be a whole bunch of answers. So had this been all answers between 0 and 2 pi on the unit circle, for all positive and negative, it's pretty much all the tangents except for the 45. So it'd be here, 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 and here. So what happens is if you had, again, from 0 to 2 pi, you would have pi 6 as an answer. You would have pi thirds as an answer. Then you would have 2 pi thirds. 2 pi thirds. Then you would have 5 pi sixths. Then you would have 7 pi sixths. Then you would have 4 pi thirds. Then you would have 5 pi thirds. And then you would finish off with 11 pi 6. So that would be all the answers between 0 and 2 pi. Now on this one, we have to see a pattern to see what we can do. So let's use a different color so you can really see it. So I have here is the same answer as these right here. That would be pi. So I'm going to add in pi, but now I'm going to take out, what was that one? 7 pi 6. So I'm taking that one out. Because I can apply that answer in an infinitely many. Again, if it's between 0 and 2 pi, it's all of these, but right now, in these first set, it's asking for all of them. Pi thirds, I can do the same concept, so I'll add in pi, and then be able to take this out, and then I can kind of finish the pattern here of what I see, and then there are your answers. So it'd be pi 6 plus n pi, and then pi thirds plus n pi, and so on and so on. Again, if it was asking for all of them, take this whole list. This right here would just be infinitely as many, or all the infinite answers. So every answer out there that applies. All right, we'll do one more in this set, and then we'll do a different type of looking problems. So let's look at number 20. Number 20 says cosine x minus 1 equals sine x. All right, so when dealing with situations like this, there's no way I could divide to make it that tangent that we saw earlier on a sine and cosine. What could I do? In my head, I'm thinking we could probably square both sides, but before I go too far, well, this one looks very similar to example 6 in the book. And that's exactly what they did. They actually squared both sides. So that's what I'm going to do too. And the reason I'm going to square both sides, because I know I can use the Pythagorean identity to potentially get rid of one of these trig functions. The goal is to get down to only one type of trig function. So again, I'm going to square both sides. Remember, this is a binomial squared, so this is the same thing as cosine x minus 1 times cosine x minus 1. This would just be sine squared x. So this would be cosine squared x minus cosine x minus cosine x plus 1 equals sine squared x. Let's see, let's clean it up a little bit. So we do cosine squared x minus 2 cosine x plus 1. And again, I'm going to use manipulation here. So the Pythagorean identity states sine squared x plus cosine squared x equals 1. Therefore, sine squared x equals 1 minus cosine squared x. So I'm going to replace sine squared x with 1 minus cosine squared x. And so now I have a trigonometric equation with only one trig equation. So now I'm just going to set it all equal to 0. Since I have this square, this is probably going to be one of those quadratic situations. So minus 1 plus cosine squared x plus cosine squared x. Again, lining up all of your like terms. This will all go away. This will now be 2 cosine squared x minus 2 cosine x, and then that actually goes away. So I don't have a trinomial anymore, so I don't got to try to do substitution, but I can do greatest common factor here. I can say, all right, well, 2 cosine x comes out, and I'm left with cosine x minus 1 equals 0. Now set each one of these equal to 0. So I'm going to divide by 2. When I do that, I still get cosine x equals 0. I'll add 1. So I get cosine x equals 1. So for this first one here, unit circle, cosine's equal to 0 and 2 spots, here and here. So that would be pi halves and 3 pi halves. And then cosine's equal to 1 in only one location, and that would be at 0. So again, looking for all your answers between 0 and 2 pi, there's your 3 answers. Looking for specifically all infinite many solutions, we want to get a little bit more specific here. So from here to here to here, there's nothing else I can do, so I can just add my 2 n pi. And then from here, I can just say n pi, because I can go from here to here to here. So this one would be n pi, which will kind of eliminate this one. And then I can kind of clean this up even more. So this would be pi halves plus n pi. And then this right here would just be 2n pi, because I don't really need the 0. Um, cosine equals 1. Hmm. They did another version, and they went with here. Ooh, fascinating. They just, I think they completely forgot about this guy, because they actually said the answer was 3 pi halves plus 2 n pi. But for 0, it happens twice, here and here, not just in this location. So I'm going to go back to that example 6 that we pulled from earlier. Ooh, certain situations. I wouldn't have thought this. All right, so okay, so what they did is they took these and back substituted in to make sure it works, since it is two different trig identities. So let me back up a little bit. Glad we got these type of problems. Um, Again, these are all the answers that would work, but now we got to go test it, see which one does work. So we'll plug in pi halves. Uh, Cosine pi halves would give me, so here again, this would be cosine pi halves minus 1 equals sine pi halves, which will just be, that would be 0 minus 1 equals 1. -1 does not equal 1. So that's why they don't have it. So that part doesn't work. So we do need to check our answers. This is just the first situation where that actually really came into play. 3 pi halves, I can see that that would just be 0 minus 1 equals -1, which does work. And then 0 would give me 0 minus 1. Oh, I lied. Hold on. Cosine of 0 is actually 1 minus 1, and then sine 0 is 0, and that does work too. So these are your two answers between 0 and 2 pi. And then to write it out infinitely, this would be 3 pi halves. Again, if that's not an answer, I would need to go the full 2n pi to get there. And then this 0 full 2n pi. So I just can write 2n pi. 0 is not necessary. So there's your answer. And I'm glad we got to one like this because you'll see one like this on your homework. All right, let's keep doing a few more to give you again some more examples. Maybe we can fall into some more pitfalls here. So let's look at number 21. This one specifically just asks for 0 to 2 pi. So again, it says use trig identities, algebraic methods, and inverse trig functions as necessary to solve the following equations between 0 and 2 pi. So I no longer have to worry about the end. I just want to make sure I gave you enough of those equations because I saw a lot of those on the homework. But now that I'm just limited to just 2 pi, I can just look at this as is. So 2 sine squared x plus 7 sine x equals 4. I just have one trig function. So I'm actually going to set this equal to 0 since I also have a quadratic. So 2 sine squared x plus 7 sine x minus 4 equals 0. Use u substitution or whatever letter you want. Doesn't really matter to me. So this becomes 2u squared plus 7u minus 4 equals 0. Let's see. So we got bang, 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 u. I'm looking for two things that multiply to 2 times -4, which is -8, but then add up to 7. Well, that looks to me like 1 and 8, where this one would be negative. So this would be -1 plus 8, and then I have to divide by my a. So, and again, if I can't reduce, it just goes to the front. So this is now 2u minus 1. And then this is just u plus 4. The whole time this was equal to 0. So 2u minus 1 equals 0. U plus 4 equals 0. Then this becomes, I would add 1, divide by 2. So u equals 1/2. And u equals -4. Substitute the sign back in there. So now I get sine x equals 1/2. Sine x equals -4. Unit circles, sine, again, I'm just looking for all answers between 0 and 2 pi now. I don't got to worry about the n. But this is between, or so this is 1/2. So sine's up here, sine x being furthest from the y-axis. So that would then be x equals pi/6 and 5 pi/6. Then I come over here, sine x equals -4. Again, hopefully you're stating, hey, sine only is between -1 and 1. So that would not be part of my solution. So in this case, I would just write pi/6, 5 pi/6, and I'm done. I don't have to worry about how many times in a circle or half a circle or any of those different type of things. That is what my answer would be. Alrighty, so let's look at some more. Let's look at number 22. So this is going to be tan squared x equals tan x plus 6. Again, I'm looking at this. There's one trig function. I see a square, so I'm thinking quadratic. So I'm going to subtract everything over to the other side. So this will give me tan squared x minus tan x minus 6 equals 0. Again, use substitution. So I get u squared minus u minus 6 equals 0. What multiplies to -6 adds up to -1. I'm thinking 3 and 2. This would be a negative. This would be a positive. That multiplies to -6, adds up to -3. This becomes u minus 3 equals 0 and u plus 2 equals 0. So this is u equals 3, u equals -2. But as I look at this, oh, sorry, my bad. Now I got to look at tangent. So this is actually tangent. I was about to look at this as sine and cosine. This is tangent equals 3. And tangent x equals -2. Now, tangent doesn't have a maximum limit of what tangent can be. So therefore, these answers would just be tan inverse of 3, because that's technically what we've been doing this whole time. And this would be tan inverse of -2. We don't know what the answer is, but it wants the exact answer, so we have to leave it like this. So when you don't have a perfect one, because remember, tangents, perfect ones are like square root of 3, square root of 3 over 3, and then 1. And of course, you can have 0 or undefined type of situation there. But this one, since tangent's not blocked. Oh, sorry. Um, we just write it like this, and it doesn't want decimals, so we leave it as such. Let's look at another situation. So let's look at number 24. This one is secant squared x minus 3 equals negative tangent x. Again, the goal is always to try to get it into one trig function. And since I have a tangent that really can't change into much, I do have something I could use for secant squared. So if you go to your Pythagorean identities, I just had it in my head and this lost. I'm pretty sure this is an 8.1. Maybe it is. All right. In 8.1, we saw a Pythagorean theorem like this one here. So it's like tangent squared x plus 1 equals secant squared x. So therefore, what I'm going to do is I'm actually going to substitute this secant squared with this tangent squared. So then I would have a trigonometric equation with only one trig function. So this now becomes tan squared x plus 1 minus 3 equals negative tangent x. Now I'm going to solve this like I would a quadratic where I need to set it equal to 0. So I'd move this over. So this becomes tan squared x plus tan x. And then this right here, 1 minus 3 gives me negative 2 equals 0. U substitution, so u would equal tan x. And so when I work this out, I would get u. Two things that multiply to 2 but add up to 1. That's only 1 and 2, so this has to be a positive, this has to be a negative. So this would be u minus 1 equals 0, u plus 2 equals 0, so this would be u equals 1, u equals negative 2, so therefore this would be tan x equals 1, and tan x equals negative 2. Now we saw a situation like this, so we want to make sure the answers that we get does work out for this. All right, tangent equals 1 when both sine and cosine are both the same value. So that happens here and happens here. But because we're looking for all answers between 0 and 2 pi, we include all answers. So this would be pi fourth. And this is 1, 2, 3, 4, 5 pi fourths. And of course, this would just be tan inverse of negative 2. And I think that's it. So yeah, and actually in this situation, I guess you don't um, got back substitute in, but I think it actually works out anyways. If you plug in pi fours, you probably do. But pi fourths, when you plug it in for secant, secant is the inverse of cosine. So that'd be 2 over square root of 2. So that becomes square root of 2. So square root of 2 minus 3 would be negative 1. And then negative 1. So pi force would work. 5 pi force would also work. Because of that square icon. So it ends up just being a positive again. So these two both work out. And then if I plug that in, I know this right here would apply to 2. When you apply inside of a secant squared of tan inverse of negative 2, you would almost have to do a triangle. So we'll just test that theory to make sure it's okay. We'll call it alpha for right now. Is OS, so this would be 2 and 1. For tangent to be negative, it has to either be in the first, second, or fourth quadrant. Both of them won't be it. We're testing I guess it won't really matter. We'll try, yeah, it won't matter because I'll square it anyways. So negative, so this would be 4, this would be square root of 5. All right, so then secant is the inverse of cosine. Cosine would be opposite over hypotenuse. Now it's hypotenuse over, oh, I lied. No, cosine's adjacent over hypotenuse. Flip that. Now it's hypotenuse over the adjacent. So that's going to be negative square root of 5. Squaring that, that would give you 5 minus 3, which would be 2 because this tan inverse of negative 2, negative would be 2. So this will work out. A lot of extra work, but we don't want to be tricked like we did last time. So do definitely go through the process and check it to make sure it does work. But those are your answers there. All right, that was a good one there. Let's look at a couple more in the situation. So let's look at number 26. 26 is 12 sine x minus 1 equals 8 sine x. Again, my goal is to get this to one trig function. So I'm going to subtract 8 sine x on both sides. That would give me 4 sine x minus 1 equals 0. Now I can isolate my trig function. Divide by 4. And then once again, I don't actually have this value on the unit circle. And again, they want the exact answer. So you just leave it as sine inverse of 1/4. Right? And then just leave it like that and you're good to go. All right, now we're going to look at number 30, and this will be the last of this set, and I'll try to show some different ones. This says sine of negative x equals 5 sine x minus 3. So in this right here, you got to remember your even odd functions. So sine negative x is the same thing as negative sine x equals 5 sine x minus 3. Do the same concept. I guess it really doesn't matter. I'm just going to move my trig function to the other side. I was saying you don't have to deal with negatives. You could bring that and that, but then you have to do it twice. So this gives you negative 6 sine x. Remember, there's an imaginary one there. Equals negative 3 divided by the negative 6. So sine x equals 1/2. That happens twice. That happens again furthest from the y value here and here. So that would be x equals pi 6th and 5 pi 6th. And there you go. Again, it's really nice when you don't have to, you find all the infinite ones. When it says 0 to 2 pi, it's really nice. All right, I did find one type of problem that we can kind of look at on number 34. You'll have some of these type of questions, but I didn't really find any in the book that were as easy as the ones given in your work. But this right here is just basically just saying, given some values, does it work? And it's true or false. It's or a yes or a no. And so it wants us to check x equals pi ninths and x equals 2 pi ninths. So all we got to do when you're given this type of question on the homework is just plug it in. So tan squared 3 times pi ninths equals 3. So this will become tan squared of pi thirds equals 3. At pi thirds, which is located right here, this would be square root 3, nope, 1/2 square root 3 over 2. Keep change flip. This would just be the square root of 3 squared, 3, and then that would cancel. So 3 equals 3, and you would verify. Then you do the same thing to the other one. Tan squared 3 times 2 pi ninths equals 3. So this would be tan squared 2 pi thirds equals 3. Again, that would be this answer. So that would be negative 1/2 square root 3 over 2. And you would get the same thing, but just negative. So this would just be negative square root of 3 squared equals 3. And a negative squared and square root all just cancels and you get the same result. So all you got to do on questions like that is simply just check it and then you're done. Does it work or does it not? All right, so now to kind of switch gears, you will then be seeing questions like number 55, where it says use trig identities in algebra as necessary to rewrite the following equations to quadratic like and then solve it. And we've been kind of doing that already, but in a more specific way. Cosine 2x equal, oh, not equal, minus cosine x equals 0. So again, on this one, when we were trying to do it earlier, we were trying to use the double angle. So if we go back to the beginning of 8.3, this is where you would want to use it. And again, I want just one trig function. So I'm actually going to choose the one that just has a cosine since that's what this is. So again, I'm going to replace cosine 2x with the double angle identity, which is one of them is 2 cosine squared x minus 1. And I'm choosing the one with just a cosine since in my equation I have just a cosine. This will give me the ability to solve something with just one trig function using substitution. So this becomes 2 cosine squared x minus cosine x minus 1 equals 0. Using substitution, I now get 2u squared minus u minus 1. And then using my quadratics, my AC would be 2 times negative 1, which is negative 2, and my B is negative 1. So I know it's 1 and 2, and then I would want this to be negative. So this multiplies to negative 2, adds up to negative 1. So plus 1, negative 2. So I get u plus 1 equals 0, u minus 2 equals 0. U equals negative 1, U equals 2. And then now plug back cosine in. Cosine equals negative 1 right here. So x equals pi. Cosine doesn't equal 2. So here my only answer would be at pi. Fascinating. That is not what they got. And we checked that cosine of 2 pi would be 0 minus 1. That would not work. Why didn't this work? Let's go back to our trig identity. Did I type it in correctly or write it down correctly? Let's see. Again, that's 2 cosine squared minus 1. That definitely looks good. I moved it over to put it in the right format. Oh gosh, I forgot a crucial step, and hopefully y'all were yelling the whole time going, I don't think that's how you do it. When there's an A in factoring, you have to divide by 2. And if I can't simplify, I move it over here. So this is 2u plus 1, and this will be u minus 1. So then that becomes 2u plus 1 equals 0, u minus 1 equals 0. So this ends up being subtract 1 divided by 2. Bring your work over here. So this will now be cosine x equals negative 1/2, and cosine x equals 1. All right, so again, unit circle. Cosine is negative on the left side, and that happens furthest from the x-axis. So that's going to happen here and here. So that would be x equals 2 pi thirds, and then this is 4 pi thirds. And then cosine x equals 1 right here. So this will be x equals 0. So there's your answers. Totally forgot that step. So watch out for that because then it gets clean. Now, granted, what I did is I took that pi and I plugged it in, and I saw that cosine of 2 pi was 1, but cosine of pi is negative 1. So therefore, 1 plus 1 would give me 2, not 0. So then I was like, oh, I definitely did something wrong. So I had to go back and check. All right, so that's good. I'm glad we're making mistakes and then learning from them. So let's look at number 58. This one is pretty much what we've been doing with 0 to 2 pi. The only difference is it wants the answer as 0 to 360. So same process as your answer is going to change at the very end. Plus it gives us some more examples to look at. Now in this one here, I'm going to do greatest common factor because I just want to get it down to just one trig function in each set. Now I can set each one of these factors equal to 0. So this now gives me, all right, where does cosine x equal 0? It equals here and here. So that's x equals pi halves and 3 pi halves. Here I would need to add 1. So sine squared x equals 1. Then the square root of that, don't forget the plus or minus. So sine x equals plus or minus 1. And that also happens to be at those two values. So it works out for both situations. But because it says from 0 to 360, you just need to say, all right, this is actually 90 degrees and 270 degrees. So same process as the answer changes at the very end. Let's do a couple more of those so you have it. Let's look at number 61. 2 sine x equals cosecant x plus 1. All right, when dealing with something like this, I don't like the cosecant. I want to get it to just one trig function. I bet we could. So let's do this. Let's do 2 sine x. I know cosecant's reciprocal identity is 1 over sine x plus 1. I don't like fractions, so I'll multiply everything by sine x. And when I do that, I would get 2 sine squared x equals 1 plus sine x. So again, that would square it. This would cancel, leaving you with the 1, and then sine x times 1 would give you this. Now I have something that I can turn into a quadratic. So 2 sine squared x minus sine x minus 1, because you change the sign when you bring them over. Substitution. So 2u squared minus u minus 1. So this would be u. We're not going to make the mistake again. So 2 times negative 1 is negative 2. I want to add to negative 1. So it has to be this. So plus 1 minus 2. Now divide these by 2. Couldn't reduce. So this is 2u plus 1. This becomes u minus 1. So this becomes 2u plus 1 equals 0. U minus 1 equals 0. So u equals negative 1/2, u equals 1. Bring the work over here, substitute it back in. So sine x equals negative 1/2 and sine x equals 1. Again, unit circle, sine is a y value, so it's going to be the third and fourth quadrant. 1/2 is small, so it's going to be closer to the x-axis. So that would give you 7 pi sixth and 11 pi sixth. X equals 1 located right here. So that's going to be x equals pi half. The only difference now, you got to plug in all of the degrees. So that would be 90 degrees. This would be 30 past 180. So that's 210 degrees. This would be 30 degrees from 360. So this would be 330 degrees. And so that's the only difference there. All right, let's do one more of that type. So 62, we get secant squared minus 2 tangent x equals 4. Again, I want to use those Pythagorean identities, which we get from 8.1, which the one I'm looking at is going to be the tan squared x plus 1 equals secant squared x. I'm going to substitute this secant squared x with this because I already have a tangent there. So I can't turn tangent into anything else. So this comes tangent squared x plus 1 minus 2 tan x equals 4. Move the 4 over, so I now get tan squared x minus 2 tan x. If I subtract 4 and I already have a 1 there, that would be a negative 3. Substitute tangent in for u. So I get u squared minus 2u minus 3. So two things that multiply to -3 has to be 3 and 1, and then this has to be negative, this has to be positive. So this would be u minus 3 equals 0, u plus 1 equals 0. So u equals 3, u equals -1. So this is really tan x equals 3 and tan x equals -1. Let's see how they want us to handle that. All right, so in this situation, because it's looking for a degree, it says find exact answers or otherwise round to 1 decimal. So I need to figure out what is tan inverse of 3 and what is tan inverse of -1. All right. So with that said, you pull up your calculator. Let's make sure I am sharing. Oh, it was up. Oh, I got a screen share. I change my view. There it is. All right, y'all seeing this now? Yeah, perfect. All right, so when I go to calculator, again, I'll do control. Actually, not even control. I think it's just trig. That's right. So it's just the trig icon. And then you just look for tan inverse. And I'm going to plug in. I do not remember what it was. I feel like it was 3 or something. I got to go back and check it. 3 and -1. All right, let's go back. 3, -1. 3 and -1. Again, make sure you are still with me. Perfect. All right, so I'm just going to plug in a 3, but the issue is I want this in degrees. So that top right-hand corner, I'm going to just hit it, and it changes to degrees. So I get an answer of 71.56. It's set around to 1 decimal, so that'd be 71.6. And then I'm just going to do the same thing. So trig, I forgot it again. I hope it's 1, but I don't remember. -1, okay. So again, I just type in a -1, it's in degrees, so there's my answer. So -45, and I guess we could have figured that one out pretty easily. All right, so let's jump back. All right, so still with me? Does look that way. All right, so then tangent would be again 71.6 degrees. Or I guess not tangent, x would be. And it was also 45 degrees. Now, the issue with these two answers here, to get a -1, this goes back to what we learned in chapter 7. Tangent falls amongst this range here. How did I get -1? Should not have been that. Hold on, let's go back and check. Did I type in a -1? I did. Oh, it gave me -45. That's it. Okay, I was about to say I should not. So -45. The issue is since I landed here, I have to add 360 because I want the answers between 0 and 360. So when I add that, that actually gives me 315 degrees, not the -45. But then also on top of that, since tangent repeats every pi, I also need to add another 180 to this one and subtract a 180 from this one so that I have all of my answers between 0 and 360. So if I add 180 to this actually gives me 251.6 degrees. And if I subtract 180 from this, I have 135 degrees. And again, we're only doing that because we want the answers from 0 to 360. And tangent repeats only from 0 to pi. So it only gave me half of the answers of a full circle. So I had to take another pi or another 180 to both of these, either by adding or subtracting to get all the answers in between it. So watch out for an answer like that. All right, this will be the last one of this one. They always like to throw in those word problems when they can, but number 70 is actually pretty straightforward. It says, if an arrow is shot by an archer with an initial velocity v0 at an angle of theta in reference to the horizontal, then its range, the horizontal distance it travels, is given by, and it basically gives you the equation, so you don't have to like worry about finding it. If the initial velocity of V0 is 100 feet per second, and the arrow hits the target 300 feet away, from where the archer is standing, so that would mean that R would be the 300. What is the value in degrees of the angle? So it wants it in degrees, but it wants the theta. Round your answer to 1 decimal place. So all we got to do is just plug everything in. So this becomes 300 equals 1 over 32 times 100 squared sine 2 theta. All right, so again, it looks complicated, but it's not too bad. So what I'm going to do is I'm actually going to switch over back to the calculator so you can kind of see it. All right, so we have 300. I'm going to multiply that by 32 on both sides to get rid of the fraction. 100 squared is 1,000, so I'm actually going to now divide that. So 9,600 divided by 100,000. Oh, my bad, just 10,000. I get this right here. And then I don't know what sine equals 24/25, so I'm going to have to now use the trig. So sine inverse 24 over 25. There's my answer, but that's what was equal to 2 theta. So therefore, I'm just going to now divide that by 2. And then there is my ultimate answer. Again, rounding to 1 decimal, so that'd be 36.9. So again, I'll show you on paper or on the whiteboard what I did to get those answers. So I first multiplied by 32. That got rid of that. And then I think that was 9,600. Then this right here, I squared it, so that gave me 10,000. So then I divide it by 10,000. This gave me a nice number of 24 over 25 equals sine inverse 2 theta. I don't know what sine is at 24/25. So what I did is I took the inverse of 24 over 25 to get me 2 theta. That gave me a number. And then whatever, I think it was 70. Crap. Hold on, give me a second. It was 73.73. Then I took that answer and I divided it by 2, which gave me my final answer of 36.9 degrees. There you go. So again, looks like a complicated word problem, but it gives you the formula, gives you all the information. You just have to solve for the unknown. If you need any more examples other than that, please reach out, let me know. That will conclude chapter 8. So your next test will be next week over chapter 7 and 8. You will notice that chapter 9 is part of this week to kind of keep us on pace. Chapter 9 will not be on next week's test. I will open the practice exam on Friday for y'all, and it'll be open for a little over a week. And then the exam itself will open up next Monday, open for 7 days. Again, can't express this enough. Don't forget to submit your work so you can get the credit for the test. Everyone's doing really good in the class, so I'm really proud. But as always, if you need help or guidance in anything in the class, over the work or the structure, just reach out to me. Other than that, see you in the next video.